There is a clay pot sitting in a village in northern Nigeria right now. No refrigerator, no electricity, no ice, and the water inside that pot is cold. Not cool. Cold. Measurably consistently cold, even when the air temperature outside climbs past 100 degrees Fahrenheit. The pot costs less than $2 to make. The materials come from the ground beneath the village. The technology behind it is approximately 4,000 years old. And it works through a principle so elegant, so grounded in basic physics, that once you understand it, you will never look at a clay pot the same way again. Today, I am going to walk you through exactly how this works, why it was nearly forgotten, and why it is now being studied seriously by engineers and humanitarian organizations around the world. The modern problem. Let us start with something most of us take entirely for granted. You open your refrigerator. The water is cold. You close the door. You never think about it again. But that refrigerator is consuming energy every single hour of every single day. In the United States, refrigeration accounts for roughly 8% of total household electricity use. That number sounds small until you multiply it across an entire country, an entire grid, an entire year. Now step outside that context entirely. According to the International Energy Agency, approximately 770 million people worldwide currently live without reliable access to electricity. Many of them live in some of the hottest climates on the planet: sub-Saharan Africa, South Asia, the Middle East, rural South America. For those communities, keeping food from spoiling and water safe to drink is not a convenience problem. It is a daily survival challenge. But here is the part that most people miss entirely. The problem of keeping things cool without electricity is not new. Human beings have been solving it in various forms for thousands of years, and one of the most effective solutions ever developed requires nothing more than clay, sand, water, and shade. The ancient method. The device is called a Zir pot in its modern revival form, but the underlying principle stretches back through centuries of practical knowledge across multiple civilizations. The concept is simple. You take two clay pots, one larger, one smaller. You place the smaller pot inside the larger one. You fill the gap between them with wet sand. You place a damp cloth over the top, and you set the whole assembly in a dry, shaded, well-ventilated space. That is the entire construction. No moving parts, no energy input, no maintenance beyond keeping the sand damp. What happens next is physics. The inner pot stays cold. Not refrigerator cold, but cold enough to preserve vegetables for days rather than hours, and cold enough to keep drinking water at a temperature that is genuinely refreshing even in extreme heat. Archaeologists have found evidence of evaporative cooling vessels in ancient Egypt dating back to roughly 2500 BCE. Paintings in Egyptian tombs show servants fanning clay jars, a deliberate technique to accelerate the cooling effect. The Romans used porous clay vessels for the same purpose. The technique appears independently across ancient Persia, the Indian subcontinent, and pre-colonial West Africa. This was not a regional curiosity. It was a universal discovery. The same physics, the same clay, the same result, arrived at separately by civilizations that never communicated with one another. That tells you something important. When multiple independent cultures converge on the same solution, you are looking at a solution that genuinely works. How it works. The science behind this is called evaporative cooling, and it is the same principle your body uses when it sweats. Here is what is happening inside the clay. Clay is a porous material. At a microscopic level, it is full of tiny channels and gaps. When you wet the outer pot or the sand between the two pots, water molecules move through those pores toward the outer surface of the clay. At the surface, those water molecules evaporate. They transition from liquid to vapor and enter the surrounding air. That transition requires energy. Specifically, it requires heat energy. And that heat has to come from somewhere. It comes from the clay itself, and from the air immediately surrounding it, and ultimately from the contents of the inner pot. As water evaporates from the surface, it carries thermal energy away with it. The clay cools, the sand cools, the inner pot cools, the contents cool. The drier and more ventilated the surrounding air, the faster the evaporation, and the greater the cooling effect. This is why the system works most powerfully in hot, dry climates, exactly the environments where keeping things cool matters most. In controlled testing, a well-constructed Zier pot in a dry climate has been shown to reduce internal temperature by 30 to 40 degrees Fahrenheit below the ambient air temperature. In a region where outdoor air sits at 104 degrees, the interior of the inner pot can reach the mid-60s. That is not approximation, that is measured, reproducible physics. Why people stopped using it? If this technology is so effective and so simple, the obvious question is why most of the world stopped using it. The answer is not a single event. It is a gradual displacement. When mechanical refrigeration became commercially available in the early 20th century and began spreading through industrialized nations, it offered something evaporative cooling cannot: consistent cold, regardless of humidity, regardless of climate, regardless of what you are storing. You could chill meat, you could store dairy, you could maintain precise controllable temperatures. For communities with reliable electricity and sufficient income, the refrigerator was a genuine upgrade. It solved problems that clay pots could not. And as refrigerators became status symbols of modern development, traditional cooling methods were gradually reclassified not as effective tools, but as markers of poverty, something to move away from, not preserve. The knowledge did not disappear entirely. It persisted in rural communities where electricity never arrived and refrigerators remained unaffordable. But it was no longer being taught, documented, or developed. The institutional memory faded. Real-life example. In 1995, a Nigerian teacher named Muhammad Ba looked at the food spoilage problem in the rural communities of northern Nigeria and decided to address it directly. He took the ancient double pot principle, refined the construction, and began distributing what he called the pot-in-pot cooler, the Zier pot in its modern form, to villages across the region. The results were documented and verified. Tomatoes that previously lasted 2 days in open air lasted up to 21 days inside the pot. Eggplant stayed fresh for 27 days. African spinach, which typically wilts within hours in extreme heat, remained usable for 12 days. For rural families, particularly women who brought produce to market and lost a significant portion of it to spoilage before they could sell it. This was not a minor improvement. It was a transformation in economic stability. Muhammad Ba received the Rolex Award for Enterprise in 2000 for this work. His project distributed over 30,000 pots across northern Nigeria. The technology was not new. The application and the documentation were. Today, organizations including UNICEF and various agricultural development agencies have studied and promoted evaporative pot cooling in food-insecure regions across Africa, South Asia, and the Middle East. How to use it today? You do not need to live in a rural village to build one of these, and you do not need specialized materials. Here is the straightforward process. You need 2 unglazed terracotta pots, one significantly larger than the other. The key word is unglazed. A glazed pot has a sealed surface that prevents water from moving through the clay. The porous raw terracotta is what makes the system function. Place the smaller pot inside the larger one. The gap between them should be roughly 1 to 2 inches on all sides. Fill that gap entirely with clean sand. Pack it reasonably firm. Saturate the sand with water. It should be thoroughly wet, not just damp. Cover the top of the inner pot with a wet cloth or a fitted lid made from natural material. Place the assembly in a shaded location with good airflow, a covered outdoor space, a shaded porch, or a well-ventilated room works well. Direct sunlight will heat the outer surface and reduce the cooling effect. Still, enclosed air will slow evaporation and reduce it further. Re-wet the sand once or twice per day, depending on the heat and dryness of your environment. In very hot, dry conditions, you may need to add water more frequently. That is the complete system. Construction time is under 10 minutes. Ongoing maintenance is minimal. What you can store inside: vegetables, fruit, drinking water, and in some conditions, certain cooked foods for short periods. What you should not expect: the sustained, precise cold of a mechanical refrigerator, or effective cooling in very high humidity environments. Limitations. This is the section that matters if you want an honest assessment rather than an enthusiastic one. Evaporative cooling has real constraints, and they are worth understanding clearly. The first is humidity. The physics only work when the surrounding air is dry enough to accept evaporating water. In humid climates, coastal regions, tropical zones, areas with high rainfall, the air is already carrying significant moisture. Evaporation slows dramatically. The cooling effect shrinks. In very high humidity, it may become negligible. This is not a flaw in the design. It is simply the boundary condition of the physics. The second limitation is temperature range. A Zir pot will not freeze water. It will not bring temperatures down to the range of a mechanical refrigerator. It is a preservation tool and a cooling tool, not a substitute for every function of modern refrigeration. The third is the need for consistent maintenance. The system requires daily attention to keep the sand wet. If the sand dries out, the evaporation stops, the cooling stops, and temperatures inside the pot will rise back toward ambient air temperature relatively quickly. For applications that require precise, humidity-independent, maintenance-free cold, commercial food storage, pharmaceutical preservation, certain medical applications, this system is not the answer. For applications that require affordable, electricity-free preservation of produce and drinking water in hot, dry climates, it is genuinely effective. Knowing the difference is the point. Conclusion. 4,000 years ago, someone in the Nile Valley noticed that a wet clay jar felt cooler than a dry one. They did not have the vocabulary to describe evaporation or thermodynamics. They did not need it. They had observation, and they had clay, and they built something that worked. That knowledge traveled through centuries and across continents. It showed up independently in civilizations that never shared a language or a trade route. It persisted in rural communities long after mechanical refrigeration made it invisible to the developed world. And now, as engineers and humanitarian organizations look seriously at the challenge of food security in off-grid communities, they keep arriving at the same place: the same clay, the same sand, the same porous surface, the same physics. There is a version of progress that means moving entirely away from what came before, and there is a version that means understanding what came before well enough to know when it still applies. The clay pot is not a relic. It is a tool, a specific tool for specific conditions with specific limits. But within those conditions, it does exactly what it has always done. It keeps the water cold. This is Dr. Lucas Grant for Prime Shelter Lab. Build smarter, depend less, keep what you earn.